says the following. That's the theorem there. So if the polynomial p of x is equal to a subscript n times x to the n plus a subscript n minus 1 times x to the n minus 1 plus, and those three dots denote other terms in between there, a1x plus a0. So those an's, the an subscript minus 1, a subscript 1, a0, those are real coefficients, okay? In fact, they are integers, okay? So they're whole numbers. They can be negative or positive numbers, right? Whole numbers. So it says, the rational zeros theorem says that if the polynomial p of x is equal to an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a0, if that has integer coefficients, then every rational zero of the polynomial is of this form, p over q, right? So every rational zero, remember a zero of a polynomial is that number or that term or that number that will make that polynomial to be equal to 0. So we call it a zero or a root of the polynomial, right? So, and in this case, so the rational zeros have this form, p over q, where p is a factor of a0, okay? And a factor means something that makes up that number, okay? And q is a factor of the leading coefficient because it's attached to the leading power. So we call this the leading coefficient. So q is a factor of that. So it's p over q. So what we'll do is look at a specific case now. So this is just a repetition from our last encounter. In fact, we worked on this example. So I want us to go through it briefly. So just bear this result in mind, okay? So if the polynomial p of x equal to an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a0 has integer coefficients, then every rational zero of p is of the form p over q, where p is a factor of that constant coefficient a0, and q is a factor of the leading coefficient an. So that's what you have to bear in mind there, okay? So for example 1 that we encountered last week, it asked you in this particular case. So this example asked you, find the rational zeros. Find the rational zeros. And the rational zeros of p of x equal to, this is x cubed minus 3x plus 2. Okay. So of course, you can see that my leading coefficient there belongs next to the x cubed, and this will be a 1 here. Okay. This is my an that we spoke of in the theorem, a subscript n. And my a0 here will be this here. And we have to look at the factors of 2 and the factors of 1. Okay. So we have to look at the factors of 2. Of course, 2. So the solution of this goes as follows. So 2 has factors plus or minus 2, and it has factors plus or minus 1. And the factors of 1 is also plus or minus 1, just like the factors of 2. So you can see when ultimately you form P over Q will look as follows. It will be either, so the factors of 2 is plus or minus 1, plus or minus 2. The factors of 1 is plus or minus 1. So it will look as follows. It will be an element of this set. We still have to decide whether these are relevant. So P of Q will either be plus or minus 1, right? Remember, it's those over those ones, or plus or minus 2. Remember, it's the P's over the Q's. So those are the 4 potential zeros of that polynomial. Okay, those are the 4 potential zeros from that theorem, the rational zeros theorem. Okay, that we constructed. Now, remember, guys, if you go back here, This is what the theorem is saying. So the form P over Q, P is a factor of A naught, that's our 2. Q is a factor of the leading coefficient AN, which is 1. Factors of 2 are plus or minus 1, plus or minus 2. The factors of 1 is plus or minus 1. So they are the factors. So now we have to test. We can test the positive values, we can test the negatives, and see when we substitute it into here. Sorry guys, when substituted into there, those values for P over Q, those four possible values, we'll see which one or which ones of those values will give us P of x equal to 0, okay? When x assume those values. So let's try P of minus 1 and see what it gives us. P of minus 1 is minus 1 cubed, minus 3 times minus 1 plus 2. So we'll do that for all 4 and check, okay? So minus 1 cubed, it's minus 1, and then plus 3. So this clearly is not equal to 0 from what I can see here, guys. It's not equal to 0 because it's 2 plus 3 is 5, minus 1 is 4. Okay, so y minus 1 is not a 0. Okay, so we're selecting from those four possible values in that curly brackets. Okay, let's try P of minus 2 now. Let's just check the minuses out. So it's minus 2 cubed, minus 3 times minus 2 plus 2. Let's see what this gives us. Well, minus 2 cubed is minus 8. And then we've got plus 6 plus 2. So this is indeed equal to 0. So minus 2 is a root. It is a 0 of that polynomial. You guys can then substitute. You can check, sorry, also for 1. What P of 1 gives us. And you will see that P of 1 gives you a 0. P of 1 gives you a 0, actually. P of 1 is equal to 0. You guys can confirm that. And P of 2 gives you also a non-zero answer. P of 2 is not equal to 0 when you do the substitution there. So the roots of interest here are minus 2 and 1. So our roots or our zeros, so our zeros or roots are the ones that give that polynomial. When you substitute them into that polynomial, it gives a value of 0. Our zeros are 1 and are minus 2 and 1. So that's how we utilize that theorem. So those are the rational zeros of that polynomial. And that's how we use that theorem, basically, okay? Looking at the factors of A naught and the factors of AN, and then putting in that form P over Q. So we had 4 possibilities there, but only 2 of them satisfy the equation P of x equal to 0. Right. So any questions at this stage, guys? Any questions before we proceed? So the rest builds up on this. It doesn't get too serious. It just builds up, but you must understand these. And then, of course, guys must remember the factor theorem also, right? For example, if I say to you a number C is a 0 of a polynomial, then x minus c is a factor of that polynomial. Okay, so if a number C is a 0 of a polynomial, right, then x minus c is a factor of that polynomial, right? So you can use your factor theorem there. So you just have to bear those things in mind. Okay, right. So there doesn't seem to be any questions. So let's go on to example 2 then. Okay. Sorry, guys. Let's go to example 2. Example 2. So this one asks you, factor the polynomial. I'll try and go a bit faster because you guys have an idea of the rational zeros theorem, okay? Factor the polynomial. So and P of x is given as 2x cubed. plus x squared minus 13x, and the last term is plus 6. And find all its zeros. Plus 6. And find all its zeros. And find all its zeros. Right, so factor the polynomial p of x equal to 2x cubed plus x squared minus 13x plus 6 and find all its zeros. So we have to factorize that. Well, we look again for that information. We remember the factor theorem. We remember the rational zeros theorem. So if you look at 6, the factors of 6, for example, that's my A0 from the theorem, the rational zeros theorem. And look at the factors of this one. We see 2 has 4 factors, plus or minus 1, plus or minus 2. And 6 has factors, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Okay. So the factors in totality, they look like this. Write down solution. So the factors look like this. Or let me say the factors of 2 and 6 combined, okay? And 6 combined, because some of them are repeating. Plus or minus 1. Those are the factors for both 2 and 6. And then 2, that's a factor for both 2 and 6. Okay, and then the factors of other factors of 6 are plus or minus 3, and then plus or minus 6. Okay, so those are what we have there. So this will give us, these factors will give us the p-value from here, the p-value, right? And you can see all those that appear there, the plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, they are all the factors of 6. And the factors of 2 are plus or minus 1, plus or minus 2. But I just include the combined factors, okay? That's all of them together. There's no need to repeat it, right? Then I just have to say one more thing. Of course, naturally, one has to do the following also. You have to now make sure you have P over Q every time and check what's happening every time. P over Q, P over Q, P over Q. And once you've done that, so these are the integer factors. Let's look at the rational factors now, okay? And the rational factors are and, so let me just insert this, and. So these are the integers. Now the rational ones are, so now I form the fractional parts. And you'll agree with me that fractional parts can be plus or minus 2, 1 over 2, sorry. And then of course, with 2 over 2, it's plus or minus 1. And then it can also be plus or minus 3 over 2. That's quite possible. Right? This is this factor of 6 over this factor of 2. Right? So P over Q. And then lastly, you can get this situation where you have plus or minus 6 over 2, plus or minus 6 over 2, plus or minus 6 over 2, which I already got there. It's plus or minus 3. So there's just a bit of repetition there, okay? But in essence, the factors are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. This is just a repetition. Here's it. I can just discard this plus or minus 6 over 2. There's no real need for that. I can just discard that one because it's already there, okay? Right. So those are all the possible, these are the factors of 2 and 6, okay? There they are. And then now for the P over Q part, these are, so what I can call this the rational zeros here. I can call this the rational zeros. So let me just say there, maybe just appropriately say the following. The rational zeros are, the factors are this, and rational zeros are, and rational zeros, sorry there guys, and the rational zeros are, then I'm just going to repeat, rational zeros are, there is the P over Q part, okay? I incorporate everything, then I just bring the top ones to the bottom again. So that will be a proper way of writing it now. Now it's the P over Q part that I'm forming. I think, yeah, I have to add this one. Yeah, I think it's proper, yeah. So those are all the ones contained in there. There are 1, 2, 3, 4, 5, 6 rational zeros, okay? Times 2, which is 12, because it's plus or minus, okay? So we have to check now, we have to check all these possible zeros, whether they are actually zeros. So we need to evaluate P at each one of them, okay? So every time you'll put in plus or minus half into P of X, plus or minus 3 over 2 into P of X, plus or minus 1 into there, plus or minus 2, plus or minus 3, plus or minus 6, and see which ones will give you a 0, okay? All right, let's, for example, check whether 1 is a 0. Let's check if 1 is a 0, okay? Well, for me to check whether 1 is a 0, I can just put 1 in there, or I can just divide and see what happens. I can just divide x minus 1 into P of X by the factor theorem, okay? If the remainder is 0, then I know 1 is a 0, okay? So if I divide x minus 1 into P of X, then I know that 1 is a 0, right? So if you actually test P of 1, let's see what we'll have. P of 1. P of 1 is equal to 2 times 1 cubed plus 1 squared minus 13 times 1 plus 6. So let's see what this yields. It's minus 7. So it's 2 plus 1 plus 6, it's 9, it's minus 4. So it's not equal to 0, right? So 1 is not a root or rational 0 of it, right? Then we can check 2. Let's check P of 2 quickly, okay? Check P of 2. P of 2, so I'm just arbitrarily checking stuff, okay? Let's check P of 2. Of course, I have to check 1, 2, 3, 4, 5, 6, 12 possible cases, okay? Right, so now I'm checking P of 2. So it's 2 times 2 cubed plus 2 squared minus 13. And this one, they say is a 0 plus 6. And they say this one is 0. Let's check. So it's minus 26 plus 6 gives us minus 20. Plus 4 is minus 16. And 2 to the 4 is 16. So this is 0, right? Therefore, x minus 2. So this 2 says to us that x minus 2 is a factor by the factor theorem. Is a factor of P of X. So we can divide x minus 2 with long division into P of X. So that P of X is now our dividend function, and our divisor function d of x is x minus 2, because we want to check what are the other factors of the polynomial P of X. So we've established that 2 is a 0, and we'll first do that division and see what happens, and see what, if we're left with maybe with some quadratic function, that's fine after this, because we're dividing a linear function x minus 2 into a quadratic. So we expect, sorry, let me say it again. We're dividing a linear factor x minus 2 into a cubic polynomial. So we're expecting a quadratic factor to appear, and then we can factorize that, okay? Right, so let's divide x minus 2 into that function. And we've discussed this at length the last time we met and the time before that. All right, you guys must just check my steps for me, please, guys. So our function is 2x cubed plus x squared. minus 13x plus 6. Minus 13x plus 6. So now we want to get the quotient, okay, and see what's happening. So we divide the divisor function x minus 2 into the dividend function 2x cubed plus x squared minus 13x plus 6. So it's the same procedure like I said like the last time. So x divides into 2x cubed 2x squared times, and then I multiply 2x squared by x and then by minus 2. So I've got 2x squared, 2x cubed, sorry, 2x cubed, and then I multiply it by 2, so it's minus 4x squared. You guys must just double check my work, and then I do a subtraction. The signs change here, signs change, and then I add. I'm doing a subtraction. Of course, with a subtraction means the bottom two term signs are changing. So that's a 0, 2x cubed minus 2x cubed. And then I've got 4x squared plus x squared is 5x squared. So in the meantime, I can maybe bring down 13x. And then I can ask, how many times does this x here divide into 5x squared here? Well, it divides into there 5x times. 5x times. And then I say 5x times x, 5x times minus 2, and so forth, so forth. Okay, so that's what I'm going to do there. Just get rid of these sticks here, guys. Okay, so now I'm multiplying x minus 2 by 5x. Let's see quickly. So x times 5x, 5x squared. And minus 2 times 5x is minus 10x. All right. And now I subtract, the signs change again. It's the same thing that happens. So I'm left with minus 3x, and I can bring the 6 down. Okay, I can bring the 6 down. And now I ask the question, how many times does this x divide into minus 3x? Well, minus 3 times. Just erase that. And now I will multiply x minus 2 by minus 3. So I've got minus 3x. And then minus 2 times that is plus 6. And of course, you guys can see the remainder 0. So by the factor theorem, I can now say, well, by the remainder theorem, I can say x 2x cubed plus x squared minus 13x plus 6 is equal to that linear factor x minus 2. Remember, I put the 2 in there and I found the p of 2 is 0. So x minus 2 is affected by the factor theorem. And then on top, it yielded this quotient function, 2x squared plus 5x minus 3. Now we see if we can maybe perhaps do a factorization of that. Okay, if we can perhaps do a factorization of that. Let's check if we can factorize it. I think you guys are okay with factorization, guys. So let's see. That's already a linear factor, the first factor, so we can't simplify that further. And let's see this one here, guys. If we do a factorization of this one here, right? So we've got 2x times x. And then we can see that the 3, we can put the 3 there. And then here we can put a 1. Right, then it's just the judicious choice now. We can just see if we can judiciously put it in there. And let's see what we have. Where do we put the, so it's, oh, okay, guys, I see here, I can put minus, I can put the 1 here, 3 the other side. That will make more sense. Otherwise, I'll run into trouble. Just double check for me, guys. I think I can put a 3 here. Right, and there's a plus. And here I can put the 1. Let's just check if it works out here. So let's just see if we can get the top part there. So 2x times x is 2x squared. The middle term is minus x plus 6x gives you 5x. And then minus 1 times 3 is that. It's equal to that. So clearly, for this to be equal to 0, x equal to 2, or x equal to a half, or x equal to -3. And remember what we said, guys. We said the possible roots, the possible zeros were, here they are. The possible zeros were these ones. All the rational zeros were these ones. And look, 2 is there. A half, what is that? What did we find? 2 is there, right? There's 2. A half is there. -3 is there. So those are the zeros, okay? So we factorized it, and then the zeros of P are those ones. Therefore, the required zeros, the required zeros. So we use the factor theorem to give us all the possible zeros, but then the required zeros that fulfill the requirement that when you substitute them in the place of x will give you P of x equal to 0. Required zeros are 2 half -3. Right? Great, guys. So so that's where we are. Okay. Oh, but it's -3. I say -1/3. -3. Sorry, guys. -3. Sorry for that. So guys, you don't have to check each and every one of those 12 zeros, okay? Just substitute and see which ones are likely to fit that description. I like to start with the integers. It's easier to do the calculations with, and you could see that 1 didn't give you a 0. 1 is not a 0, but 2 gave you a 0. So therefore I could stop and say, okay, now I divide x minus 2. I know of all the possible rational zeros. I know they are there. There are 12 possibilities, plus or minus r, plus minus 3 over 2, plus minus 1, plus minus 2, plus minus 3, plus minus 6 from the rational zeros theorem. And then I check the integer 1, it doesn't work. I check the integer 2, it works. So x minus 2 is a factor. And then I divide it into there. And then I ended up with some quadratic polynomial, and I could factorize it without bothering further. Okay. Okay, guys. So let me just check if there are any compelling questions that you guys have before I proceed with example 3. Example 3, and then we come to Descartes' rule. And I want us to do possibly another, I think 1, 2, 3 or 4 problems, 4 more problems, so at least. You guys, any questions there? Okay, it seems that you guys are fine with it. Let me just pause at this point, guys. Maybe before I proceed. Let's say after this, the next problem, before we start the Descartes rule, I want to encourage you to ask me any other questions that you guys perhaps have encountered. Maybe on complex numbers. I don't know. You work at different rates, okay? At a different pace. So feel free to do that. Let me just discuss this one. But let me also say that it goes in the same way, okay? It goes in exactly the same way as the previous one. Actually, I should maybe put this to you to check this one for me, to go through that example, and perhaps I can ask you some questions on it when we meet again. So what I want you to consider is the following problem. You'll do it in exactly the same fashion. It's just that this one has some 2 irrational roots, okay? Algebraic roots. 1 plus or minus the square root of 2, okay? So I'll put this example to, I'll put this example 3, and you guys can access that example, study it. So this is for your edification, okay? So I would suggest you can discuss it, if there's anything you don't understand, you let me know. And so with this example, they're asking you, again, same question. Let P of x equal to, so here's a 4th degree polynomial. We had a 3rd degree polynomial, okay? Minus 5x cubed. I'll discuss it maybe with you a quarter of the way and stop. 5x squared plus 23x plus 10. Don't worry about the sketch of this graph now, guys. Okay. I'm not sure how much your lecture attached to the importance of the graph sketching, because there are graph sketching devices. And besides, when you do the next level of maths, you'll use what we call the notions of differentiation, derivatives, and do curve sketching using derivatives. Okay. Because the methods that they're discussing here are a bit outdated. So using the derivative methods are much faster. Okay. So, but anyway, so the first question was saying find the zeros of P, and the next question sketch the graph of P. So I'm still establish how serious sketching the graph is using these older methods. So there's P of X, so fourth degree polynomial. And here, A4, my leading coefficient A4 is equal to 1, and A0, constant coefficient there is equal to 10. Of course, you'll have plus or minus 1 is a factor of 1. Plus or minus 1 is also a factor of 10. And then there are also plus or minus 5, plus or minus 2. Okay, so the possible zeros are the following. Remember, you say you want to form P over Q. So the factors are, and the P over Qs are. So the factors are, the combined factors are. So for 1, it's plus or minus 1, which is also the same for 10. Okay. 10 has factors plus or minus 2 in addition to plus or minus 1. And it has factors plus or minus 5 in addition to plus or minus 10. So 10 has 8 factors and 1 is 2 factors, okay? Right. And you can see if you say 10 over 1, 10 over plus or minus 1 is plus or minus 10. Plus or minus 5 over plus or minus 1 is plus or minus 5. And plus or minus 2 over plus or minus 1 is plus or minus 2. And plus or minus 1 over plus or minus 1 is plus or minus 1. So these are your factors, and they are also the zeros, by the way. Okay. The factors of, that is the factors of 1 and 10, which are also the possible zeros. Which are also by the rational zeros theorem, which are also the possible zeros. Right. Right. Of course, you can perhaps try and establish what the zeros are, and you'll see that 5 is a zero. You can perhaps start with 1 and 2, and you'll see that they're not zeros. You can substitute 1 and 2 into P of X, and you'll see 1 and 2 are not zeros. However, if you substitute 5 into there, you'll see P of 5 is equal to 0. So therefore, X minus 5 is a factor. 1 and 2, which you will verify. 1 and 2 are not zeros. They are not roots. Okay, or zeros. They are not zeros. So eliminate that. But 5 is, and we'll get others. And therefore, X minus 5 is a factor. By the factor theorem. Okay. Now, what you will do from the step onwards, you will say X minus 5. You will use your long division. And then you'll divide that linear factor X minus 5 into this, this quartic polynomial, degree 4 polynomial. Sorry, guys. I wrote this down incorrectly. Plus 23x plus 10. Plus 23x plus 10. Right. So you guys will do that long division and you'll end up with some cubic polynomial, okay? And you'll see that of course, x minus 5 is a factor, so the remainder is 0, okay? And then you'll go about in that way, and you'll establish what the other zeros are, okay? Establish. Remember, these are the rational zeros. After factorization, you might find that you come to a situation where you have a quadratic, and now you'll use your formula to find those roots. In fact, there are two other roots, 1 plus or minus the square root of 2, which are irrational roots. So this theorem will provide you with this long division. It will provide you initially the other rational zeros. We already know that 1 and 2 are not zeros. So what remains for us is 5, and we check 5 was, if you substitute it, we'll check that 5 is a 0. You check minus 5, you check plus 10, minus 10, but you don't need to do that because you know 5 is a 0, so x minus 5 is a factor. And then based on that, you divide x minus 5 into x to the 4 minus 5x cubed minus 5x squared plus 23x plus 10. And then it will come up, it will show you the other factors now, okay? After the long division. So you need to check all those roots, just like that. Okay, let me stop. Let me just pause at this point and just check if there's anyone perhaps you don't follow what I request. Guys, I trust that your silence means that you're fine with that problem, that you can proceed with it from there. Pretty much in the same way that I proceeded, okay? What I'm saying is that you will encounter two additional roots, which is not given by the rational zeros theorem, and those roots are 1 plus or minus the square root of 2. Okay. Okay. Will you guys be able to proceed with that and discussing this? Okay, can you guys maybe attempt the problem quickly and then explain to me what's happening? Okay. Okay, I think, okay, then just for the sake of completeness, let's do it together then, okay? Because I'm not sure how to interpret your silence. Fine. Ms. Brun, can you see the screen? Hi, Ms. Brun. Guys, can you see the screen? Okay, great. Okay. Thanks, Prince.
Yes, sir. Yes.
Thanks, Prince. Thanks. Okay, so what I will do is then, for the sake of completeness, guys, let's do this long division quickly, okay? Like I said to you, this is like an algorithm. So you follow the same sequence of steps, okay? So let's see. So you ask yourself, this x minus 5. So we've checked P of 5, P of 5. I don't know if you guys have verified it, but P of 5 is equal to 0, okay? So 5 is, so P of 5 is equal to 0. You guys can verify that. And if P of 5 is equal to 0, this means that x minus 5 is a factor. Okay. If that's the case, it means that x minus 5 is a factor. So now we want to see the other actual zeros from this long division now. Okay. So the question is, how many times does x divide into x to the 4? Well, it divides into there x cubed times. Right? And then I do the multiplication again. Same procedure. Okay, same procedure. And then I multiply x times x cubed is x to the 4. And I say negative 5 times x cubed is negative 5x cubed. And I subtract, okay? And I subtract. So I think I wrote down everything correctly. Let me just double check. 5x minus that plus 23x plus 10. Yeah, otherwise there will be big problems. Then I subtract and everything works out nicely. As I can see, this is just 0. And then I can bring down my minus 5x squared. I can bring down my minus 5x squared plus 23 if I want to 23x. And then I say, okay, x divides into minus 5x squared. X divides into minus 5x squared, right? Minus 5x times, right? And
Sorry,
again,
sir, are you writing? I'm not seeing anything on my side. I don't know if it's only me.
Is it? Oh, guys, there's just a question whether the rest of you can see the screen.
No, sir, we can't see the screen.
Oh, okay. Wow, thanks for that. Guys, you must warn me early. Let me just stop sharing and then possibly a connection problem. Let me share again. Okay. Are you able to see it now?
Yes, thank you.
Okay. Let me just. I'm not sure at what point I lost you guys now. So I'm just going to start again. I'm not sure where I lost you. So anyway, so we've established that P of 5 is 0, that 5 is a root of that polynomial. So therefore, x minus 5 is affected by the factor theorem. Now we ask the question, okay, how many times does x divide into x to the 4? Well, it goes there x cubed times, right? Just erase this here. And now again, like we did with the previous long divisions, we do this again. So we say, okay, x goes into x to the 4 x cubed times, x times x cubed is x to the 4. And minus 5 times x cubed is minus 5x cubed. And then I do a subtraction again. That will give me 0, okay? And then in the interim, I bring down the negative 5x squared. And possibly I can also, if I want to, I can bring down to 23x, okay? And then the question is again, how many times does this x divide into minus 5x squared? Okay? It divides in there minus 5x times. And again, I do the multiplication. All right? I do the multiplication. So let's see. So x times minus 5x is minus 5x squared. And then minus 5 times minus 5 is plus 25. And then I do my subtraction. There's a sign change. There's a sign change there. And here I've got minus 2x. Then I bring down the 10. Bring down the 10. Then I ask myself, how many times does this x divide into minus 2x? I say, well, minus 2 times. Okay. And then we then do the following. We multiply again. Minus 2 times x. Minus 2 times x is minus 2x. And then minus 5 times minus 2 is plus 10. And clearly you guys can see that the remainder is 0 when you do the subtraction there, right? The remainder is 0. So we found another factor. We found the quotient. Therefore, currently we have that polynomial, that 4th degree or quartic polynomial, x to the 4 minus 5x cubed minus 5x squared plus 23x plus 10. That may be written as a linear factor x minus 5 multiplied by a cubic polynomial or cubic factor, x cubed minus 5x minus 2, right? So that's where we are currently. And now we investigate this polynomial alone. Let's investigate this one. And see, there's the a naught. Now we use the rational zeros theorem again. There's the a n, it's 1. Okay? So the factors of 1 are plus or minus 1. And the factors of minus 2 are plus or minus 2. Okay? Right. So again, consider x cubed minus 5x minus 2. And you'll see that the possible candidates here now, the possible zeros are the divisors of minus 2, because minus 2 has divisor plus or minus 1, just like this one here has possible divisors plus or minus 1. So possible zeros are, using the rational zeros theorem. So possible zeros are plus or minus 1 and plus or minus 2. So there are 4 possible zeros there, okay? Right. And we can possibly say, okay, we know already that 1 and 2, from our early encounters, we said 1 and 2 are not zeros. Yeah. So we will only consider -1 and -2 and see what happens, okay? Right. So possible zeros are, but however, from the above, we know that 1 and 2 are not zeros, right? But 1 and 2 are not, but 1 and 2 are not zeros. Are not zeros, right? So when you substitute into that original polynomial, you'll see they we don't consider them. So consider -1 and -2. So when you put -1 into here, what do you get? You put 1 into there, -1 into there. Well, let's see quickly what that will give us. Well, let's just see if we put -1. Consider, sorry there, guys. Consider P, so -1. So I'll put it in here. We'll put it in this one here, into that bracket. So -1 cubed -5. We can even put it in the bigger polynomial of degree 4. Okay, the polynomial with bigger degree, sorry, with degree 4. It should give us 0 or not a 0, just like that. So testing it on the cubic polynomial is as good as testing it on the quartic polynomial. So I'm testing -1 of that, +2, and let's see what we have. So we have -1 plus 5. So we can see that this is not equal to 0. So we try -2 now. So -2 should be our 0. So -2 cubed, right? -2 cubed, -5 times -2 -2. Let's see what we have there. So we have -8 plus 10. -8 plus 10 minus 2 gives us 0. So we can see that -2 is indeed a root. It's a 0 of, in fact, it's a 0 of x to the 4 minus 5x cubed minus 5x squared plus 23x plus 10. If it's a 0 of this here, then it's a 0 of the polynomial with greater degree also. You can test that, okay? And if that's the case, therefore, x plus 2 is a factor. If -2 is 0, then therefore x plus 2 is a factor. Right. And then we can divide x plus 2. Remember, we're looking at this smaller polynomial now, this one here. We'll divide x plus 2 into that and see what we get. Okay? So that's what we'll do. Let's see. So let's divide x plus 2 into the smaller one here, the smaller degree polynomial, this one here. And let's see what we get. Thus, x plus 2. Okay. And we divide it into x cubed minus 5x minus 2. X cubed minus 5x minus 2. Right. So we divide it into there. So x goes into x cubed, x squared times. And then we multiply x plus 2 by x squared, which yields x cubed. sorry, x cubed plus 2x squared. Then we do a subtraction, and we see that x cubed minus, remember there's a sign change there, and we know the degrees of those polynomials are not the same there, the 2x squared and the 5x, so that I will have minus 2x squared minus 5x. All right. Now I ask myself, how many times does x go into minus 2x squared? It goes in there minus 2x times. And then I repeat the process. I multiply again. I multiply x by minus 2x, and I multiply 2 by minus 2x. So let's just see what we get. Let's just see what we get there. So we have.
Excuse me, sir.
Just hang on. Just hang on.
Can I
Minus
just
2x
ask something?
Okay, did I miss something? Did I mess something up?
Yeah, I think so.
Oh,
Because
okay.
like the
Let me see. Let me
signs
just.
like
Let me
didn't
just.
change.
Yeah. Let me just check quickly. Did I write down the factors correctly? Sorry, there was just some noise in the background that disturbed me. Just want to check quickly. Okay. So it goes in the x squared, so it's x cubed plus 2x squared. So I'm subtracting. So that gives me minus 5x. Yeah. Okay. So I'm asking how many times does it go in there? Minus 2x. So plus 5x. Okay. So it seems fine. It seems fine. Huh? Everything seems fine. I'm just multiplying out now. Okay. So I'm multiplying x plus 2 by minus 2x. Okay. So I'm having minus 4x, and then I'm subtracting again, so that I'm having minus x, and then I bring the minus 2 down, right? I'm bringing the minus 2 down. Now I ask myself, how many times does x divide into minus x? Minus 1 times, right? Divides in the minus 1 times. And then I multiply minus 1 again by x plus 2. And I get minus x minus 2, and subtraction gives me 0. So ultimately, you can write x cubed minus 5x minus 2 as x plus 2 times that. So you will substitute in the place of this here. You'll put there, in there, you'll put x plus 2 times x squared minus 2x plus 1. So the whole thing may be written as, therefore the whole thing, so from here, you can clearly see that x plus 2 multiplied by x squared minus 2x gives you that product, x cubed minus 5x minus 2, okay? That's what you can see. So in totality, the quadratic polynomial, or the polynomial of degree 4, may be written as, the original thing was minus 5x cubed, okay? Minus 5x squared plus 23x plus 10. Plus 10. And that, well, we initially wrote it as, we remember we got 5 as a factor there, so sorry, x minus 5 is a 0, so x minus 5 is a factor. And then we split up the cubic polynomial into x plus 2 times x squared minus 2x minus 1. So we can see that so 5 is a factor and minus 2 is a factor. But here, when we use the formula, the quadratic formula here, you will see that 2 irrational roots will come up. The one root, when you use the formula, x equal to minus b plus or minus the square root of b squared minus 4ac over 2a, you will see that the factors here, using the formula, and I want you guys to practice it quickly and check if you agree. So here the factors are, when you factorize, when you use the formula, So using the formula, you'll see, remember the formula says x, because you can't factorize that, right? Because the discriminant delta is not a perfect square. So x equal to minus b plus or minus the square root of b squared minus 4ac over 2a. Now you identify your a and your b. Your a is 1, your b is minus 2, and your c is minus 1. And then, of course, your zeros will be, then you guys will verify if you get those zeros the same, those irrational zeros. So we are interested in the totality of zeros. So the zeros are, we had 5, and then we can see it's minus 2. And then using the formula, the quadratic formula, you'll see the other two roots are 1 plus or minus the square root of 2. Plus or minus the square root of 2. Right. So those are your zeros, guys, okay? Right, so I just want to come back to the question that was asked. I wasn't sure. I thought I'd made an error or something, but it seems fine. Okay. What was the question there, guys? Any questions there, guys? The last person, sorry, man, I thought you were trying to correct me on something, but I saw I was on the correct path there. Are you clarified now on your question? Guys, can you hear me?
Yes, sir. Yeah,
Okay.
we are good.
Great. Yeah. But there was a lady student that asked, okay, Lebogang says I can't see the screen. That was earlier, no? Okay, no, that notion of the recordings you can deal with Ms. Prim on that, guys. Okay, that's an administrative question. Okay, so I'm not going to entertain that question, Lebogang. Okay, right. Ms. Prim deals with those issues. She can respond to you on that. Okay, right. So, but I wanted to check from the lady student what the question was initially. Okay. Nothing. Okay, great. If there are no questions, okay, guys, any other questions that you want? With regard to the recordings, you can speak to Ms. Prim, guys, okay? Can everyone see the screen currently, guys? Can everyone see the screen? Is it okay?
Yes, sir, we can.
Great, thanks. So I can only surmise that the lady who asked the question, the lady student, I suppose the question was answered then, okay? Right. So now I just want to say something about Descartes' rule of signs and upper and lower bounds for roots. Okay. So we have to consider. So yes, the Descartes, the French philosopher and mathematician, developed a way to establish a lower and an upper bound as to where an interval where the roots should lie. Okay, and he based it on a change of sign rule. They call it Descartes' rule of signs. So, and it's called a variation of sign. Okay. So this is, you would write the powers in descending order. So for example, so let me just introduce the section and call it, let me just call it Descartes' rule of signs and upper and lower bounds for roots. So Descartes' rule of signs Descartes' rule of signs and upper and lower bounds for roots. And upper and lower bounds sorry guys, and lower bounds for roots. Okay. Right, upper and lower bounds for roots. So let me just try and illustrate the rule of signs, Descartes' rule of signs, and then we'll discuss the notion of an upper and a lower bound for the roots. Okay. So so if you consider a polynomial, p of x equal to 5x to the 7 minus 3x to the 5 so minus 3x to the 5. So basically you check how the signs vary, and that tells you later on you'll see how it comes into play when you check for the upper and lower bounds of the roots. In what interval the roots are lying, okay? So 2x squared plus x minus 3 plus x plus x minus 3, okay? And then, so you can see that the powers are descending here. You guys can see the powers are descending, x to the 7, x to the 5, x to the 4, x squared, x to the 1. And then there's minus 3 times x to the 0, which is minus 3 times 1. So and now you can see that the coefficient signs are changing from positive to negative, from negative to positive, and then from positive to negative. So there are three variations in sign happening there. So here there are 3 variations in sign, okay? From the highest to the lowest powers, there are 3 variations in sign, right? Right. So there are 3 variations in sign. 3 variations in sign, okay? 3 variations in sign. Okay, great. Great. So, so there it was arranged the terms from, it was arranged in descending order. And then you see 5 is positive, 3 is negative, 1 is negative, 2 is positive. The coefficient of x is 1, it's positive. And then the constant coefficient is negative. So 3 variations in sign. So now let me state the rule properly, what it says exactly, okay? So now we come to the actual rule, and this rule helps you to determine. So it says something about the number of positive real zeros. It helps you to determine in the long run. Just after this, you'll see how to determine from this the upper and lower bounds where the roots are lying. Okay. So let me just say Descartes' rule of sign. So we have to. This is very important. So you want to be able to sort of restrict your roots and see that it lies in this interval on the real line, okay? Descartes' rule of sign. Right, Descartes' rule of sign. Right. Okay. Right. Descartes' rule of sign. So it goes as follows, guys, and then I'll explain it quickly, okay? So it says, let P be a polynomial with real coefficients. So let P be a polynomial So let P be a polynomial with real coefficients. I don't know why the pen is acting up again. I fixed up the software. Polynomial with real coefficients. With real coefficients, okay? So the coefficients are real numbers, right? So those ANs, AN minus 1, A1, A0, they are real numbers. So they're not just integers, they are any real number, okay? So that's the requirement there. Right. Okay, guys, let me just see. I'm not sure what is happening here. Erase that. Oh, that is even stuck. Okay, guys, let's see quickly. Right, so the real coefficients. So right. Okay, can you guys still see the screen, I guess? So let P be a polynomial with real coefficients, okay? Just want to see if you guys can still see the screen. Okay, great. Okay, guys. Okay, okay, student Mampejo. Yeah, thanks, student Mampoto. Student Mampejo. Your hand is raised there.
Oh yeah, it's a mistake, sir. Just
Oh, it's a mistake. Okay, okay.
Yeah.
And I think the one student info indicated that they can see the screen. Okay. Sorry guys, I'm not sure what's happening with the pin. I thought I sorted out the drivers, everything. I'm just a bit frustrated with this pen now, but it's not the pen, it must be something else. Settings, I'm not sure. So let P be a polynomial with real coefficients. And then the first point is as follows. It says 1. The number of positive real zeros, number I'll just say number NO dot, number of positive real zeros. I'll say positive, I'll just say a plus sign, number of positive, okay, so just shorthand notation, number of positive real zeros, and maybe I can just explain this, real zeros, number of positive real zeros of P of X, of P, either is equal to either either is equal to the number of variations in sign in P, just explain this one, guys. Variations, number of variations in sign in P, sign or is less than by an even whole number, or is less than or is less than or is less than by an even whole number. By an even whole number. Okay. Just you guys an even whole number. Okay. So people, I just put the number NO dot. Okay. So let's just read the first one, Descartes' rule of sign. So let P be a polynomial. So like pretty much the stuff that you've dealt with, x to the 4 plus 5x cubed, those are polynomials. X cubed plus whatever, x squared, those are quadratic, cubic, and quartic polynomials. Okay. So now we say the coefficients, those a naughts, a1, a2, an, etc. They are real numbers. Okay. Then they say the number of real zeros. So the zeros that satisfy that polynomial, that are real numbers, they're positive real numbers. Number of positive real zeros of P either is equal to the number of variations. Remember on top there for P of X, we had 3 variations. When we arrange the powers in descending order, we encounter 3 variations in sign. So they say the number of positive real zeros of P either is equal to the number of variations in sign in P, okay, or is less than by an even whole number. We'll explain that when we come to that, okay. What's an even whole number? 2, 4, 6, etc. Okay, 2, 4, 6, 8, etc. Right. And the second point, so this will become clearer when we deal with an actual example. And let's check the second point. Second point speaks of P of minus X. Okay. It says the number, and I'll say NO dot, says that the number of negative real zeros, number of negative real zeros, and I'll just say negative for the sign, number of negative real zeros, right? Real zeros of P is either equal to the number of variations in sign
Please,
guys.
I can't see
okay.
your screen.
Is it okay? Okay, I think I don't know. The writing takes some time to get through. Okay, okay. So what can you see it now? The number of negative real zeros of P. Okay, let me just see if I can change things again. Oh no, okay, I understand. My screen is freezed up again. Okay, it's freezed. Okay, because I can't even go to the icons to erase and stuff. Let me just okay. Okay. It's freezed up. Okay, that's why. Can you guys read what I've can you read what I've written on the on the whiteboard? Because now it's freezed up on my side.
The last words are variations in sign in.
Okay, okay. I'm sorry, guys. In P of minus X, and now it's. I think my screen is freezed up now. Okay. Okay. The number of negative real zeros of P. So what we'll do is, guys, this will become clearer when we do an actual example. Okay. So let me just say, and we'll keep this on here, or is less than that by an even whole number, or is less than that, is less than that, there's the sign for less than, by an even whole number, right? By an even whole number. And we'll encounter a particular case. Right. Or is less than that by an even whole number. Okay. Right. I don't know. I'm trying to do the sort of the icons here, but I don't know. An even whole number. Let me just say NO, okay? Let's erase that and say NO. Okay, so we've got those two, or the one rule with two sections to it. And it will become clearer. So Descartes' rule of sign states, so for P, a polynomial function with real coefficients, so those A(n), A1, A0, etc., those are real numbers. And it says the number of positive real zeros. So we know what's a zero. If you substitute that in the place of X, we get P of that number equal to 0. So the number of real zeros of P either is equal to the number of variations in sign, which I've just shown you on top there, variations in sign. There we have 3 variations in sign after arranging the powers in descending order. So it's either equal to the number of variations in sign in P, or is less than that by an even whole number, 2, 4, 6, 8, etc. And then the number of negative real zeros of P. So you have negative zeros also, you have positive zeros, but the number of negative real zeros, so -2, -4.6, whatever, it's a real number. So the number of negative real zeros of P is either equal to the number of variations in sign in P of minus X, right? Or is less than that by an even whole number, okay? So when we'll come to a specific case now and use it, right, okay? Right, so let's just check the notion of variation in sign quickly for example 4, and then we discuss upper and lower bounds, and then we can maybe stop there. So let's just do this example quickly to illustrate points 1 and 2 above, okay? So let me just do example. So this is Descartes' rule of signs. So let's look at example 4. Okay. Example 4. Example 4. Let's look at example 4. Okay. Right. Let's see quickly. Okay. Right. Okay, guys, so let's consider this and see if we can apply Descartes' rule to this case here. Oh, sorry, guys. So now it's shifted, and I was throwing the line far below that. So, okay, let's see, okay. Let's see. Okay, so we have to use Descartes' rule of signs to determine the possible number of positive and negative real zeros of the polynomial. Okay, so for this example, P of x. So the question here, guys, is use Descartes' sign rule or rule of signs to determine the possible number of positive and negative real zeros of this polynomial. Okay, so using the above rule of Descartes, right? We must determine the possible number of positive and negative real zeros of the following polynomial. Right? P of x equal to 3x to the 6 plus 4x to the 5 plus 4x to the 5 okay, now it's phrased up on me again now. Plus 4x to the 5 right, x to the 5 plus 3x cubed minus x minus 3. Okay, guys, so there we have 3x to the 6 plus 4x to the 5 plus 3x cubed minus x minus 3, okay? So we have to use Descartes' rule of signs to determine the possible number of positive and negative real zeros of that polynomial, remember? So there's the rule. The number of positive real zeros of P either is equal to the number of variations in sign in P, or is less than that by an even whole number. So there we had a polynomial, for example, of 7th degree, and we saw there are 3, and then, like I said, it was arranged in descending order, descending powers, from x to the 7 up to x to the 0, which is minus 3x to the 0, okay? X to the 0 is 1, you know that, guys, okay? So there we encountered 3 variations in signs when we look at the coefficient signs: positive, negative, negative, positive, positive, negative, okay? So we had 3 variations in sign. So Descartes' rule speaks of that. If you want the number of positive real zeros of P, it's either equal to the number of variations in sign in P, or is less than that by an even whole number. So let's look at the first point there, okay? And then compare it with what we have in front of us, right? So if you look there, if you look at the positive part, if you look at P of x only, P of x only there, what do you see there in terms of variation in sign there, guys? You see all these ones are positive. 3 is positive. 4 is positive. 3 is positive. Look, there's one variation in sign here. Look, there's one variation in sign. There's it. Okay. Yeah. It is arranged in descending order. Right? It is arranged in descending order. There's nothing to compare this one with here. So you can see that 3 is positive, 4 is positive, 3 is positive, minus 1, it's negative. So you have one variation in sign. So it's one variation. Okay? Right. So this one variation means there's one positive 0. It's one variation. Let me just say one var. So I say one variation in sign, okay? Therefore, it has one positive 0 plus P has one positive 0. Right. So there's only one variation there. So P has one positive 0. Okay. That's all you can say there. There's nothing else you can conclude there. And then my screen got stuck again, guys. Yeah. Okay. Can you guys still see the screen, I guess? Can you guys still see the screen?
Yes.
Okay, great, great. So I'm looking at point 1 of Descartes' rule of sign, guys. Sorry for this. Really, I have to see these guys again at work. Okay, so P has one positive real root. Okay, that's what we can say there. But the whole thing is stuck now, so I'm not sure. Okay, great. There it comes up. Sure. Okay, guys, it's fine. It seems to be okay now. Okay, great. Sorry for that. So it's one variation in sign. One variation in sign. Right. So it's one variation in sign here. Right. Meaning from point 1, P has one positive 0, right? So if you look at that point, it says is equal to the number of variations in sign. The number of positive real zeros is either equal to the number of variations in sign, which we have 1, or is less than by an even whole number. The first even whole number is 2, and if you say it's less than by 2, you already have one positive real 0. So if you say 1 minus 2, it's -1, which doesn't make sense, okay? Or it's less than by an even whole number. So what we can say that P has one positive 0. That's what we can say there. Then the next point is the number of negative real zeros of P is either equal to the number of variations in sign in P of minus x, or is less than that by an even whole number. So let's get P of minus x, guys. Let's get P of minus x now. So wherever we see x, we substitute it with minus x, okay? So let's get P of minus x quickly. So let's just see. P of minus x. So we will substitute P of minus x wherever we see x. We put a negative x there, right? And we know what is a negative. We know what's a negative to an even number. It's positive. And to an odd number, it's negative, right? So there you can see 3 times negative x to the 6. So you can see that will just be positive. But anyway, let me write it down. 3, and then we multiply inside there. So I have minus x all to the 6. Minus x all to the 6, okay? All to the 6. Right. and then we say plus 4. Plus 4. So we know that minus x to the 6 is x to the 6, right? And then we've got plus 4, and then we've got minus x to the 5. This is minus 4x to the 5, okay? Minus 4x to the 5. So now we take that and we raise it to the exponent 5. And the same will happen with the x cubed. It will also be minus. Okay, and then we check the change in signs there. So now we encounter the coefficient 3, and inside there, we replace the x with minus x, all cubed. Okay, minus 3, and we say And inside there, we say minus x all cubed. Minus x, okay, and we cube that. And then we say minus, and x must be replaced by a negative. There's already a negative in front of it. And then I must put another negative x inside the bracket there. And you guys can just verify my calculations. And then, of course, minus 3 is unaffected. It's a constant. It's a constant coefficient. So I don't anticipate that changing. In fact, it's not changing, of course. So let's just see there. Right. And now, from our experience with multiplication by odd and even numbers, multiplying negatives by odd and even numbers, we know that this here will just be 3x to the 6. 3x to the 6. And the next term will be minus 4x to the 5. The next term will be minus 4x to the 5. And the next term, minus 3x cubed. Minus 4x, because minus times a minus times a minus 5 times is minus 1. Sorry there, guys. Right. So we'll have 3x to the 6 minus 4x to the 5 minus 3x cubed plus x minus 3. And now we'll check the number of variations in sign there. Okay. We'll check the number of variations in sign there, in that case. Right. Okay. What's happening? The screen is frozen again. Okay, great. Okay, guys, let's check the variations in sign quickly. So we can see there's one variation in sign. 3 is positive, 4 is negative. It's one variation. And then look what happens here now. Look what happens here. Here's another variation. And here's another variation, yeah. Here's another variation, yeah. Can you see here? Remember here I said to you that 3 there was no variation. There's minus 1 there. There's a minus 1. So there was no variation from minus 1 to minus 3. So that's why we couldn't add that one. We couldn't add that one. So there we said for p of x, there was only one variation in sign, okay? Because minus x, the minus 1 is negative, minus 3 is negative. And here we've got two variations, yeah, 3 variations, sorry. So there's one variation. And here's a variation minus 3 to positive 1. And here's another variation, positive 1 to minus 3. So we've got 3 variations in sign, okay? Yeah. So now this is an interesting case. So the rule says that the number of negative real zeros of p is either equal to the number of variations in sign in p of minus x. We picked up 3 variations in sign, or is less than that by an even whole number. So in the next even whole, the first even whole number is 2. So you will find that here there are either 3, you've got either 3 or 1 negative real root. Okay, we have 3, because now you say 3 minus 2, which is the first even whole number. So you have 3 or 3 minus 2, which is equal to 1. Or 1 negative real zero. Okay, guys, there's that, okay? So when we dealt with p by minus x by virtue of this rule, we saw that they said, look at the number of variations. We found 3 variations. 1 plus 1 plus 1 is 3. And then Descartes' rule says, I'm trying to just go up with the screen here. I seem not to be able to do that. Okay, So Descartes' rule says it's either that or it's 2 less, or it's an even number less, which is 2, and 3 minus 2 is 1. So in the case of P of minus x, you have 3 negative, real zeros, or you've got 1 negative real zero. Okay, I think yeah. So it's 3 or 1 negative real zero. That's the situation there. Using Descartes' rule, the second point there. Okay, so you have 3 or 1 negative real root, or real zero. Right. So it's either 3 negatives or 1 negative real root. Yeah, I can just say 3 negatives or 1 negative real zero. Right? 3 negative real zeros or 1 negative real zero. Right, guys, let me allow for questions, and then I'll stop writing now because this is becoming a bit of a frustration. Okay? So any questions that you guys have regarding Descartes' rule, guys? Okay. Any questions there? Remember that we had 3 variations in sign, and then Descartes' rule says it's the number of variations in sign in P of minus x always less than that by an even whole number, and the first even whole number is 2, so it's 3 minus 2 is 1. Those are for the negative real roots. Okay. In the first instance, we only had 1 variation in sign. So if you subtract the first even whole number, that's 2. So 1 minus 2 is minus 1. So it doesn't make sense. So you will say in the first case, for P of x, it will have 1 positive real root. Okay. Right. Okay, guys, any questions there? So the next time we meet, I just want us to discuss upper and lower bounds, to maybe do 1 or 2 problems and start with complex numbers. Okay. So you maybe do 2 problems and do complex numbers, and start with the importance of the complex numbers is that not all roots of polynomials are real numbers or real roots. Some of them are complex roots. So they've got a real part and a so-called imaginary part. Okay. Right. So we'll discuss that whole notion and possibly the operations also with the complex numbers. Right. Okay, guys.